We're now back and ready to wrap up this example, the solution to this example. A reminder, we had this two-story, two-bay rigid frame with lateral loads applied to them, and we were asked to figure out the maximum axial forces, shear forces, internal bending moments, and the reactions. Okay? So we've done all the work. The previous parts to this video, I believe it's 1, 2, and 3, are linked below in the description. Similarly, you'll find in the description also the link to the video describing the assumptions for inflection points for portal frames, a link to the solution to example 0, which is an introduction, and I highly recommend you review. And finally, a link to a PDF document with the full written out solution to this. Okay, so you can review it there as well. So what I'm doing now is wrapping it up with the final answer, the results, and I'm going to have the axial and shear summary and the bending moment summary. So this will include also reactions and reactions. If this is looking new, check out example 0 for how we did it there as a good introduction. What I'm going to do too is, because I'm going to show the axial and shear forces in the members, columns and beams, at the location of the inflection points, I'm basically going to just erase enough space to show that, okay? Right here, right here, and then right here. Okay? So basically, I'm just making room for myself to write in axial and shear forces in here at the location of these inflection points. Okay? So, let's start with, how about this set of columns? We know these columns are in tension. We found that out from our previous work. So I know this is tension, tension, right? Because these forces are pulling on the column. And then here we get tension, tension, right? Tensile forces, because they're pulling on the column, on the inflection point, right? Remember, all forces, tension or compression, are always with respect to the joint. And because we're showing these at the inflection points, they're pulling on the inflection point, okay? We found that the axial forces here are 0, so I'm just going to show them in some direction. Mostly, I picked tension, but it could be compression, but mostly so I don't forget to write that it's 0. Okay, so see, I'm showing that force in tension because it's pulling on the inflection point. And the forces along these columns were in compression. So look at this. Up, down, right? This force compressing, like that. And I'll write down the magnitudes in a moment. Okay? I'm just going to look them up on this PDF solution that I've linked for you. So this here is 3, 3, 15, 15. This one here is the same, just in compression. So 3, 3, 15, 15. So notice how I'm not differentiating with a positive and negative whether they're in tension or compression. I'm doing it with my arrows, so with the direction of my vectors. Now I'm also going to show the interstory shears, right? So that's this, this, like that. And I'm showing both the direction, if I'm looking at this from this point, and this direction if I'm looking at it from this point. Okay? And a reminder to myself about what these interstory shears are. This is 5, 5, this is 10, and this one here is 15, 30, and 15. Now I'm showing them in different colors only so it's obvious to you which ones I'm labeling and indicating. You don't have to do it in different colors, right? When you're looking to submit this work for grades, I'm okay if you do it all in pencil, okay? Especially if it's a test, you may not have the opportunity to switch colors. Now that we've done the columns, let's do the beams. So all the beams we found were in compression. So all the beams look like this. Don't forget, compression is always with respect to the joint. So with respect to that inflection point. Okay? And the compressive forces at the top are 15 and 5. So this is 15, 15, 5, 5. And at the bottom, 30 and 10. So 30, 30, 10, 10. And now I'm also going to add the shears in here. And the shears are all like this. In this case, because that's what we found. And again, the shear directions are based on whether or not we're looking at this shear for this portion, or the same shear but looked at it from this here. So the shear at the top were 3 and 3. And at the bottom, I believe there were 12 and 12. And finally, the reaction forces. I'm going to show it here. Reaction, this is 15. This is 15. This is 30. This is 0. I'm just showing it so that I don't forget about it, okay? But if you didn't show it, that'd be technically okay. Although I prefer if you did, even if it's 0. This is 15. Okay, so A, D, H, X and Y forces. Great, we're done. And you don't have to put in the magnitude, sorry, the units, because we put them up here. Axial and shear forces for the whole thing, done. Getting to this point is the majority of the work. Doing the bending moment diagram, if you remember from example 0, is the easiest thing in the world. So if you haven't checked it out, check out example 0 for how we did it there. So the way to figure out the bending moment diagrams is simply to always do shear times that half distance. I'm first going to show my reactions here for the bending moments, which we found previously. The reactions here are all in this direction. Okay? And as we call them here, these are positive moments. I want to point out that in the PDF file, the document that I linked for you with the full description, I have a different convention for positive moment. So that makes no difference to you, but I want you to be aware of because I prepared this solution a year or so ago. Okay? And we picked this convention in class. Okay, so this here, the moment reactions are 22.5, 45, 22.5. Okay. So the idea here is that we want to find the internal moments at each end of the members. So we want to find here at the top of beam, column AB, here at the bottom of BC, here to the left of BE, and so on and so forth. And the way we do that is the shear times that distance. The shear times that distance, which is the half distance. So in this case, the moment there is going to be 15 times that distance, which is 1.5. 15 times 1.5 is 22.5. And what do we have to do? We have to figure out the direction. This shear, the top one, right? This shear is trying to go like this, clockwise. That means the reaction moment has to be counterclockwise. Counterclockwise is like that, positive. Okay? Okay, let's do the bottom of this beam. It's going to be this shear, right, the bottom shear times that half distance. So it's 5 times 1.5. That's 7.5, right? So this here is 7.5 at the bottom of that beam. Is that positive or negative? Well, let's check it out. This shear is trying to turn this way, which is clockwise. That means the reaction here has to be counterclockwise. The reaction there at the moment has to be counterclockwise, therefore positive. Okay, now let's find the moment at this end of beam BE. It's going to be this shear times this half distance. That shear is 12 times 25. What is 12 times 25? Sorry, 2.5. 12 times 2.5. 30. So the moment here, the internal moment at the end of that beam is 30 kilonewton meters. Now we have to figure out the direction. This shear is going up. So it's trying to turn this part of the beam this way, which is counterclockwise. That means that this end here must balance it out, must react with a clockwise moment. A clockwise moment is the opposite of that. It's negative, which is great because look at this. The moments here balance out to 0. You don't want an unbalanced moment at this joint. Otherwise, it means that a part of the beam is going to snap off, right? You want them all to balance out. It also means that your analysis is incorrect. If that happens and it's a test, don't sweat it, okay? Only go back to check and find your mistake if you have time. If you don't, continue doing it, okay? Just because it doesn't balance out, it doesn't mean your submission is 0. It does in real life, but this is not real life when it comes to tests. Okay, let's move on. The moment here at this end is also going to be 7.5. Okay. Again, 5 times 1.5 is 7.5. This is trying to cause a negative moment, right, a clockwise moment. So the reaction here is counterclockwise, positive. Okay. At this end here, we're going to get 3 times 2.5, which is 7.5. And this shear is trying to cause a counterclockwise moment with respect to that. That means you need a clockwise moment here to react it. Clockwise is negative, which is good, right? You see how we get a 0 balance here? Okay, equilibrium. If we proceed in that fashion as well, we're going to get that this here is minus 30, minus 7.5, minus 7.5, 15. Okay, so check it out. See if you can get these same answers, right? See how this balances out to 0, where negative is clockwise and positive is counterclockwise. So this end here is 15. This end here is 30. Okay, so this 15 refers to the bottom of this column. That minus 30 is that end of the beam. Okay, so use the same process. See if you can get the same answers. So what I want to do maybe together, how about we, I don't know, confirm this 15 here at the bottom of that column. It's going to be the bottom shear 10 times this half distance 1.5, so that's 15. This shear is trying to cause a clockwise moment. That means the reaction here must be counterclockwise, positive. That's why it's positive 15. You see, it's practice. Practice it out and you can rock the heck out of it. Okay? So give it a try. Practice, practice, practice is your friend. What I want to talk about for a moment is this. Notice how all these columns are tension, all these columns are compression, and this middle column is 0. Okay. Well, does that make sense? Well, these supports are fixed, right? They can't rotate, they can't move side to side, they can't move up or down. If I'm pushing sideways, let's pretend this were a chair or a table. If I'm pushing sideways, what I'm trying to do is basically tip this over, right? It wants to fall over. The only way that this falls over is if this end lifts up, right? The only way this tips over is this moves up, tips over. That means I have to pull it back down to make sure it doesn't move. And that's why this reaction goes down, it's pulling down, and all these columns are in tension, okay? Now conversely, if this wants to tip over, that means I'm trying to push this end into the ground. So that means that because this can't move, right, it can't go into the ground has to push back up as a reaction. And that's what you get right here, a push up. As a result, all of these columns are getting squished, right? Because it wants to tip over, the ground pushes up, and you're getting compression. That's why all of these columns are in compression. Now, what's happening here? The columns in this structure go from the very outside in tension to the very outside on the other side in compression. Somewhere between here, to go from tension to compression, your columns have to go through 0. And that happens in the middle columns. Okay, so that's why these columns have 0 force. Now, that doesn't mean that these columns are useless. It simply means for these applied forces, using this method, you get 0. Now, obviously, if people are living here or working here, there are different loads to consider as well, and that will give rise to forces in that column. Okay? I think we're going to cut it here, and thank you for your time.